Alright, today we will start on flip-flops. Later on we will check the shift registers part. Uh, the D flip-flop, I am talking about D flip-flop today, and so we know that all D flip-flops are always edge triggered, and the outputs. What does this mean that flip-flops are edge triggered? This means that output changes only at the clock edge, and we can have two kinds of clock edge. Either it can be a positive edge or it can be negative edge. So the flop can be a positive edge triggered flop or a negative edge triggered flop. Also, the this edge where the clock is the data output is changing, that clock edge is known as active edge. Moreover, flops can have reset or set pins, and some flops do not have set and reset pins. So, what is a reset pin? When this reset is asserted, then the flip-flop's output becomes 0. And when the set is asserted, the flip-flop output becomes 1. Now, coming to types of set and reset, we can have active high reset or active low reset. Where active high means output will become 0 uh, when reset equals to 1, and active low reset is when output becomes 0 when the reset is 0. Apart from this category, we can also have we can also classify reset as synchronous and asynchronous. So synchronous resets are those uh, in which the output changes only on the active edge of clock. So what we do is we assert the reset, and then we wait for active edge of clock to come. When the active edge comes, only then the output will change. And the second type is asynchronous reset, where the output changes as soon as the reset is asserted. It does not depend on the clock. Similarly, we have similar categories for set and set, and this can be active high set or an active low set, which means the output will become 1 when set equals to 1, and the in the active low type, the output will become 1 when set becomes 0. And similar to synchronous asynchronous reset, we have synchronous asynchronous set, where synchronous set is the one in which output changes at active edge of clock, and asynchronous set is when the output changes as soon as set is asserted. So based on these categories, we can have several types of D flip flop. Uh, so we have three categories. One is active edge of clock, like is it a positive edge triggered flop or is it a negative edge triggered flop. Then we can have a set and reset, like is there a set or reset available. So for that we have four categories, like no set or reset is available, then only set is available but no reset is available, then only reset is available and no set is available, and finally both set and resets are available. Now these set and reset can be either active high or can be active low. So one example could be positive edge triggered flip flop with with only reset and no set, and the reset is active high reset. That is one possibility. Another possibility can be negative edge triggered flop with only set, and the set is active high set. So Similarly, we can follow these arrows to deduce all types of D flip-flops. Now we will take a look at Verilog code for a simple D flip-flop. So I have here two flops. One is a positive edge triggered flop and other is negative edge triggered flop. And these two flops are not having set or reset pins. So the Verilog code for such a flip-flop would be, first we will declare a 1-bit register by the name Q, and then we will make it as a positive edge triggered. So the flop will be changing its value at the positive edge of the signal by the name clock, CLK. So always at pos edge CLK, Q, non-blocking assignment D. Similarly, in negative edge triggered flop, we are declaring a 1-bit register Q. We are assigning D to Q non-blocking in a non-blocking manner, and we are doing that at neg edge of the signal CLK. So always at neg edge CLK, Q non-blocking assignment D. And here are the symbols of positive edge triggered flop and negative edge triggered flop. Observe the bubble at negative edge triggered flop's clock input. Now let us take another Verilog code example of D flip-flop with the reset. So we can have two types of reset, that is synchronous reset and asynchronous reset. And again we can also have a category of active high reset and active low reset. So here I will talk about out of the four combinations, I'll talk about two of them, which is synchronous active high reset and asynchronous active low reset. So first we will take a look at uh, asynchronous active low reset. Just like previous implementation of D flip flop, I have declared a register 1-bit register Q, and uh, I am changing the value of Q on the positive edge of clock, or else I want the value to change at negative edge of reset n. This is RSTN n. I mean RSTN reset n, right? So uh, if I'm putting reset n in the sensitivity list, this means that the reset will occur without regard for clock, because here we have written a or keyword, right? Okay, so let's understand this bit of code here. Here we have a whenever a neg edge of reset n comes, okay, then we will be executing the this bit of code. And if you see, we have a if statement with the reset n negated. So suppose there is a negative edge of reset n coming, then we know that reset n equal to 0, which means this part will be executed. So Q will be assigned a value of 1 tick B 0, which means when the negative edge of reset n comes, the output of flop is becoming 0. So this is acting like a active low asynchronous reset. And if it is not 0, if the reset n is not 0, then the output Q will become same as input D in. When will this case be possible? It is possible only when reset n is not 0. Okay, so that condition comes from this part, and reset n is not 0, and we get a positive edge of clock. So the significance of this negage reset n statement comes only in this first part, which is if not reset n. Okay, so this is the uh, act, active low asynchronous reset, and I have a diagram of this. We have a positive edge triggered clock as indicated by lack of bubble here, and we have a active low asynchronous reset as indicated by a bubble over here. Now let's take a look at synchronous reset, which is active high. Okay, so if we take a look at the always statement here and compare it with the previous case, we observe that there is no negage reset n present in the sensitivity list, which means that all the changes on the output of flop will occur only on the positive edge of clock. And if we see the previous requirement for active, synchronous and asynchronous, we see that if output changes at only at the active edge of clock, then it is a synchronous reset. So we have a synchronous reset over here. Now how is this working? So whenever positive edge of clock comes, we check the value of RST. If it is 1, then reset will happen, which means Q output Q will get a value 0. Else the output Q will get a value of D in, synchronous to the positive edge of clock. So this part of code is implemented as a mux, as a 2x1 mux, with the select line, which I have not shown here. I missed to show here, so let's put that. So with this select line as with select line as RST. Okay. Also understand that if there is a signal which is not in the sensitivity list and it is becoming a condition inside if else statement, in that case this condition acts as a mux select line, and this if else thing becomes a mux, and uh, the I0 leg, okay, the I0 leg will become the else statement, and the I1 leg will become the portion of if statement. So yeah, this was on D flip flops, and we will check the shift registers part in the next video. For practice, please try to write verilog codes for remaining types of D flip flops. And if you have any doubt, please put that in the comments.